Hello, everyone, thanks for watching this video. Today I'm going to talk about our work, overlap-guided Gaussian mixture models for point cloud registration, which is a probabilistic registration approach for point clouds with partial overlaps. Correspondence-based methods dominate state-of-the-art feature-based point cloud registration. Correspondence-based methods commonly start from local feature extraction and matching. GMM to GMM registration considers point cloud registration as matching two distributions rather than finding point-to-point correspondences. Point cloud registration is challenging in partial overlaps and density variations. Furthermore, for correspondence-based methods, the size of the correspondence search space increases quadratically with the number of points of source or target point clouds. We are motivated to apply GMM clustering in overlap regions to handle registration with partial overlaps. Given a input partial point clouds, our method detects b the overlap regions that are then used for the estimation of c the transformation that aligns the 2 point clouds. The non-overlap regions in b are shown in gray. OGMM consists of feature extraction, overlap region detection, and overlap-guided GMM for registration. The shared weighted encoder extracts point level features FP and FQ from point clouds P and Q, respectively. The self-attention module updates the point-wise features FP and FQ. The overlap region detection module projects the updated features P and Q to overlap scores OP and OQ, respectively. FP, FQ, OP, and OQ are used to estimate GMMs of P and Q. The weighted SVD estimates the rigid transformation T based on the estimated distributions. Self-attention is introduced to model global structures by establishing long-range dependencies. We exploit this idea to improve the computational complexity of self-attention. Specifically, we first use Wasserstein k-means to cluster point cloud P or Q into J non-overlapping clusters in geometric space. Using this partitioning, we can now compute the clustered attention. Cross-attention is a typical module for point cloud registration tasks, which performs feature exchange between two input point clouds. It can be accomplished by a similar way of clustered self-attention. After obtaining the learned overlap scores, we can calculate the GMM parameters based on equation 1. Our method can handle registration with partial overlaps and density variations. We perform extensive experiments and ablation studies on synthetic and real-world point cloud datasets, including the ModelNet 40, 7 scenes, and ICL NUM. Here we give an example for each dataset. We evaluate the registration quality by using the mean absolute error, MAE, between the estimated rotation angle and ground truth angle and the estimated translation and ground truth translation. We also use clipped chamfer distance, CCD, which measures how close the 2 point clouds are aligned with each other. Our method outperforms the recent correspondence-based state-of-the-art RGM and REGTR on all datasets. Compared with the GMM-based method Deep GMR, which is closest to our method, our approach also achieves the best results. Density variation reports the results when the point density is reduced to 50%. Our method can outperform the other methods when source and target point clouds have different densities. This occurs mainly because the source and target point clouds are modeled as GMMs. Therefore, the alignment between the two GMMs becomes less sensitive to density than establishing explicit point correspondence. This figure shows various successful and unsuccessful registration results. We can observe that cases with low overlap, e.g., guitar, and with repetitive structures, e.g., net, can be handled by OGMM. The most frequent unsuccessful cases involve point clouds of symmetric objects that can have multiple correct registration solutions along the symmetry axis that do not match with the ground truth one. This is an intrinsic problem of symmetric cases. The second most frequent unsuccessful cases involve point cloud pairs with repetitive local geometric structures. GMM clustering underperforms because features of similar structures in different locations have a small distance in the feature space. We presented a learning-based probabilistic registration approach for partially overlapping point clouds. We use a clustered attention-based network to detect overlap regions between 2 point clouds and formulate the registration problem as the minimization of the discrepancy between Gaussian mixtures under the guidance of the overlap information. Thank you for your attention. We will release the source code on GitHub. Any feedback is appreciated.